Hello all, myself Kalpana, Assistant Professor in Mlritm. Subject name is Electromagnetic Fields. So today I am going to explain about the Gauss law applications, Maxwell's first law, and also Laplace and Poisson'S equations. So in previous class I already explained what is the statement of the Gauss law, and again I am revising here. So according to the Gauss law, it states that the total electric flux through a closed surface is equal to the total charge enclosed by the surface. In the sense, when we are taking a point in a space, here we are assuming a charge. Okay, so here total electric flux means if it is a electrostatic field, so we have a it is charge is there means there is a flux flowing here. So this total surface, closed surface, it is a closed surface is equal to the total electric flux passing in a closed surface is equal to the total charge enclosed by that particular surface. So that is about the Gauss law. We already derived the Gauss law proof. Today I am going to explain about the applications of Gauss law. So here as part of applications, here I am taken the point charge. Okay, so I am taken one space that is XYZ. Here I am assuming a point P. Okay, here it is a point charge is located. Okay, point charge is located at the origin. At this point, I am deriving the equation for this particular electric field intensity or electric flux density. So here for this I am assuming a sphere of radius r which is having a flux density d in this radial direction. Okay, so let here modulus of d means this flux density is in the direction of radial direction. Okay, so that is equal to dr into ar, that is in ar direction. Okay, so here it is a surface we are considering. So and also we have a sphere of radius r. So total charge is enclosing in this particular area. For that I am taking the differential surface area ds, that is equal to r square sine theta d phi into ar. Why? Because it is in ar direction only, that is in a radial direction only. So I am taking the d dot ds. As per Gauss law, we know that d dot ds equal to total charge enclosed. Okay, so for that I am taken here d dot ds. D means here dr into ar, and ds is nothing but r square sine theta d phi into ar. So I am substituting this and again integrating with respect to ds. So in a total surface. So here these are the ranges. Phi is from 0 to pi and theta is from 0 to pi and phi is from 0 to 2 pi. Okay, so after deriving we will get here this total d dot ds equal to 4 pi r square into dr. So as we know that this is equal to q, that is as per Gauss law. So total charge enclosed, so d dot ds is equal to q. So from that we will get q equal to 4 pi r square into dr. So from this dr equal to q by 4 pi r square into ar. So this is the d is nothing but electric flux density. So from this we can write electric field intensity d E equal to, as we know that d equal to epsilon into E. We know that this is the relation between flux density and electric field intensity. From that we can write E equal to q by 4 pi epsilon naught r square into ar. So this is the first application of the Gauss law. So here we are consider the point charge which is located at the origin, and here we need to calculate the electric flux density due to this point charge. So next coming to the, if we consider a infinite line charge. So here I have taken a cylinder here. Okay, so it is a Gaussian surface. So this length of this cylinder is the L. So as per Gauss law, we can say that Q, that is Q is nothing but it is a charge. Total charge is nothing but, so along this total cylinder, so integral d dot ds, that is sides and top and bottom, we need to consider total charge enclosed by top surface, bottom surface and lateral surfaces. Lateral in the sense sides. So integral of side d dot ds plus top d dot ds and plus integral of bottom of d dot ds. So d equal to dr into ar, because here this charge is along the radial component only. Why? Because as we know that charge is on the surface itself, it is acting, not on the inside of the cylinder. So top and bottom are zero components. Only radial component has existing here. So ds equal to, we can write that ds equal to r into d phi into dz into ar, which is normal to the AR direction. So after substituting in d dot ds, we'll get dr into r d phi dz into here ar dot ar. Already we have dr into ar, d equal to, and ds component, this is equal to r d phi dz into ar. So we'll get dr r d phi into dz. So here these two components, you are equating it to 0. So now total charge equal to only side surface, that is d dot ds, that is nothing but dr into r d phi dz. So here we need to write the ranges. So z is from 0 to L. As we know that here length is L, and here we have one more component, that is d phi, it is a variable. So phi is from 0 to 2 pi. By substituting and integrating with respect to d phi and dz, we'll get q equal to 2 pi r into dr into L. So here from this q by L, that is total charge per unit length. Charge per unit length is nothing but, this is line charge density, rho L. We can write this as rho L. So d equal to rho L by 2 pi r into ar coulombs per meter square. So this is d is nothing but here electric flux density. Okay, so as we know that the relation between electric field intensity and electric flux density is nothing but d equal to epsilon into E. So by substituting, we'll get E equal to, that is electric field intensity equal to rho L by 2 pi epsilon naught into R AR volt per meter. So this is the charge due to electric flux density due to infinite line charge. So this is the second application of Gauss law. So next, here we are considering one sheet of charge. So for that, we are calculating the total charge enclosed by this sheet of charge. Okay, so for that, I am assuming here it is a sheet. It is having charge Q. Okay, so here, so this is a Gaussian surface. Okay, so here total charge is nothing but here side surfaces and bottom surfaces. Okay, so side surfaces, that is we can write the total charge enclosed by this total sheet of charge is nothing but integral sides d dot ds plus top surface d dot ds plus bottom surface d dot ds. Okay, and here we know that only this flux density has only component along the xy directions only, not in a sides. Okay, so for that, so for top surface, so it is along the z direction. So that is dz into az, that is a top surface, and bottom surface is opposite to this z direction, that is in minus z direction. So we can write that d equal to dz into minus az. So it is a bottom surface. Okay, so then we can write the surface area. Differential surface area is nothing but dx dy into in az direction. So that is along the minus az direction. One is, that is nothing but in the minus z direction, it is dx dy into az, and top surface it is dx dy into az, that is positive. Okay, so now we can write the total charge equal to integral top dz into dx dy plus integral bottom of dz dx dy. So here integral of top dx dy equal to bottom of dx dy equal to total area. So we can write this as A, total area. So we can write Q equal to 2 dz, we can write 2 dz into A. So here we are assuming that rho s is the surface charge density. Okay, so rho s equal to 2 dz. So from this dz equal to rho s by 2. So d as we know that it is along the z direction. So d equal to dz into az. So rho s by 2 into az. So the unit is coulombs per meter square. By writing the relation between flux density and electric field intensity, E equal to d by epsilon naught, we can write rho s by 2 epsilon naught into az volt per meters. So these are the 3 applications of Gauss law. Okay, next we will see what is the Maxwell's first equations, which is derived from the Gauss law of electrostatics. Okay, so for this here we know that Gauss law states for electricity states that the total electric flux out of the closed surface is equal to the charge enclosed by charge enclosed, which is divided by the permittivity of the medium. Okay, so here electric flux in an area can be defined as electric field multiplied by the area of the surface projected in a plane which is perpendicular to that particular electric field. So as per Gauss law electrostatics, we know that surface integral of E dot ds equal to q by epsilon naught. So by applying the divergence theorem gives that it is the relation between the surface charge and volume charge. So we can write surface integral of E dot ds equal to volume integral of this del dot E into dv. This is divergence theorem. Okay, so from these two equations we can write that here E dot ds equal to q by epsilon naught. So volume integral of del dot E dv equal to q by epsilon naught into dv. So here we know that volume charge density Q is nothing but volume integral of rho into dv. Okay, so from this both the integrals are cancelled. So we can write that del dot E equal to rho by epsilon naught, which is the Maxwell's first equation, which is derived from the Gauss law of electrostatics. So this is the Maxwell's first equation for which is derived from Gauss law of electrostatics. So next we'll see the Poisson'S and Laplace equations. So in part of that we'll see first what is the Poisson'S equation. So here this Poisson equation is also derived from the Gauss law. So according to Gauss law, we know that divergence of the electric flux density is equal to the charge density, that is del dot D equal to rho v. Okay, so as we know that D equal to epsilon into E, so which gives the relation between electric field intensity and flux density. So by substituting D equal to epsilon E in del dot D equal to rho v, we'll get epsilon into del dot E equal to rho v. So from this we can write that del dot E equal to rho v by epsilon. But we know that E equal to minus del into v. Okay, so by substituting this in this above equation, we'll get del dot E equal to rho del square v equal to minus rho v by epsilon. So this equation is the Poisson's equation, which is derived from the Gauss law of electrostatics. So next we'll see the Laplace equations. So here we have Cartesian coordinate system and spherical coordinate system and also cylindrical coordinate system. So we are representing this Laplace equation in these three coordinate systems. So first of all we'll see the Cartesian coordinate system. So for that, del of del v, we'll write dou by dou x of dou v by dou x plus dou by dou y of dou v by dou y plus dou by dou z of dou v by dou z. So from that we can write that del square v equal to dou square v by dou x square plus dou square v by dou y and plus dou square v by dou z. So as we know that del square v equal to already we derived for Poisson'S equation minus rho v by epsilon. So equating these two equations, we'll get del square v equal to minus rho v by epsilon. So this is the Cartesian coordinate system in which is the Laplace equation in Cartesian coordinate system. So next we'll see the cylindrical coordinate system. So here we have in cylindrical coordinate system coordinates of rho, phi and z. So for these three coordinates are represented like this in del v, that is divergence. So 1 by rho into dou by dou rho of rho into dou v by dou x plus 1 by rho square into dou square v by dou phi square plus dou square v by dou z square. So this is the del square v. Okay. So now next, as we know that del square v already derived from the Laplace equation, that is del square v equal to minus rho v by epsilon. So then we'll represent in cylindrical coordinate system this particular equation equal to minus rho v by epsilon. So this is the Laplace equation in cylindrical coordinate system. So next, spherical coordinate system. Here coordinates are r, theta and phi. So we are representing this divergence of this r, theta, phi like this form, and del square v equal to 1 by r square into dou by dou r of r square into dou v by dou r plus 1 by r square sin theta into dou by dou theta of sin theta into dou v by dou theta plus 1 by r square into sin square theta into dou square v by dou phi square. So as we know that from the Laplace equation, del square v equal to Poisson equation, del square v equal to minus rho v by epsilon. By substituting, we'll get del square v equal to minus rho v by epsilon. Okay, but if the volume charge density is 0, then del square v equal to 0. Why? Because rho v is 0. So when rho v is 0, del square v also 0. This operator is called Laplacian operator, and del square v equal to 0 is nothing but it is a Laplace equation. Thank you. I am taken references from William Heath and also Sadiku book and also AU Bakshi and VU Bakshi. So this completes the module 1. So in the next class, we'll discuss about the module 2. Thank you.